and some of this stuff we can go through kind of quickly. There are the section 3-5. I'm going to tell you, we're going to get into this hopefully today. This gets a little more complicated. It has to do with a third variable, z, where you have two random variables, x and y. And it becomes something that can be a lot more abstract. You know what convolution is? Everybody has to have it. All right, basically, you're going to be doing operations that are exactly parallel to convolution. And one thing you remember, I'm just setting the stage for this one. Do you remember when you had signals and systems that if you had some h of t that was the impulse response of a linear system, a circuit typically, that if you had an input x of t, you could get the output by convolving x of t with h of t, you could get y of t. You all remember that? That was the brute force hard way usually. What did you normally do to solve that problem? I mean, any kind of a problem where you have an input and a impulse response. You went to the frequency domain. Do you remember you went x of omega times h of omega is y of omega? That was much easier than to take y omega and do the inverse transform and get h of t. Usually, I'm saying this is from personal experience. Convolution can be mind-bending and painful a lot of times when you're flipping, shifting, and you get the overlapped areas and you have 3 or 4 different regions you have to worry about. And that's my approach to section 3.5. I'm telling you ahead of time, I'm going to show you something they call the characteristic function in our book or in this PDF. It is exactly the same thing as the Fourier transform with one sign. You remember how when you do Fourier transforms, you have f of t e to the minus j omega t dt, and you integrate from minus infinity? Well, the characteristics function is f of t times e to the plus j omega t. So basically, everything's the same except the sign. I'm just setting you up for this because you're going to have to at least appreciate this very shortly. Now, back to section 3.4. Here, how many actually took a look at this? I know we're coming off of July 4th. If you haven't, be attentive here. Do you all remember when we talked about things, we started, oh my gosh, this is going back 3 weeks. We started with something when we talked about the mean squared value, the mean value, and then the standard deviation, or I should say the variance. Do you all remember that? We're going to talk about something called the covariance today. So let me set this up. When you have the variance of anything, variance of x, for instance, variance of x, the symbol for that was sigma of x squared. Do y'all remember? And do you remember what exactly that was mathematically? What was what? An integral from what? Minus infinity to infinity of x minus x bar squared, right? It's that, and it's going to be times, if you take a look at this, f of x dx for the variance. Do y'all remember this class? All right, I mean, basically it's expected value. The way I'm going to put this down for the variance, it's the expected value, which is that integral, of x minus x bar squared. Well, it's called the variance. The covariance, and I can spell the whole thing out, the covariance of two, it won't be one, of two things, say covariance of x, y. It's very similar to the variance. Here's the difference. Now it's going to be the expected value of x minus x bar as here, but then it'll be y minus y bar. So it's basically the same thing as a variance, only now the second thing we multiply it by is the value of y, which is a second random variable that can or can't be related to the first. Do y'all hear me? And we're going to get something called a covariance. Have you heard of covariance in any of your classes? Anywhere? You have. All right. Now, the covariance tells you something that's important. It tells you the relationship of one to the other. And I'm going to do this in a bit. I'll bring up the PDF or the PowerPoint of this in a bit, but I want to just kind of make my point. Whenever you have a function, say x, y, these can be random variables. if you see something like this, you would say the general trend is positive. Y'all follow me? And if it went the other way, you know, if it was something like this, you would say the general trend is negative. X related to Y has a negative, it's called a correlation coefficient. And if you had something like this, it would be flat or linear. That would be a correlation coefficient of 0, but there's still a relationship between X and Y. Y does not vary with X. Do y'all follow me on this? Then there's something, this is sort of a scatter plot. If this is X and Y, and you have just something where nothing is related to anything, then the correlation coefficient will also be 0. It'll be 0 for what's called a flat line and something random. Now, here's what I'm going to tell you. And I'm trying to get to the point as clear as possible. But this is what a correlation coefficient tells you that he doesn't come right out with. So the real problem with covariance is that it doesn't include anything that scales these with something called with standard deviations of both. Follow me? So if we take, I don't know where this, I'm going to try to give you a page number in the PDF so you can look at it. If, this is on page 132, it's equation 3-24. If you just write it down, it'll help you see what my point is. So if you went ahead and now you took the expected value of X minus X bar times Y minus Y bar. Now again, that's the covariance, but then you divided it by sigma X, sigma Y. What that will do is scale everything. And this whole thing is going to be related to something called the correlation coefficient. Correlation coefficient. And they always put a sub x, y, because it's talking of, you'll have the correlation coefficient between the two variables. Follow me? And he has that, I think, stated explicitly.
And that's a row, right?
Yeah, it's rho. And this is equation 3-25, if you look at it. Well, it's actually 3-24, and I'm going to expand this. So here's the normal way this is shown. This is the one you need to remember. When you get rho of xy, what that is the expected value of x times y. Now, you'll notice the mean is not broken. You're not taking expected value. It's not the covariance of x minus x bar, y minus y. Expect y minus x bar, y bar, and then they'll have sigma x, sigma y. This is important. And that's a correlation coefficient. And that is 3-25 in the book. Now there's some, if you look at page 133 in your book, he goes through and he substitutes certain things. He tries to get it down to a nice compact kind of a handy-dandy formula. I wouldn't worry about that. But I want to say a few more things about it. So why do we want this? Is because with random variables, and you get, this is just two, but you can get a huge number of variables. What you like to see is statistically important relationships, one to the other. For instance, in my world, radar cross-section, I would love to see the relationship to, well, let me be very clear about this. Target accuracy related to clutter, the clutter signature, and I can't specify this more than what I'm saying. I want a relationship between that, and there is for this stuff. But there's also things like radar cross section correlates very well with the shape of objects. A round ball that's conducting coming at you is very easy to see. If you have something with a needle nose, and it had, I mean, like it's almost going to a stealth design where you're going to have reflective properties, it's very hard to see something with the same, you might say, area, cross-sectional area looking at it. Because it reflects the signal. There's a lot of stuff on this. And there are correlation coefficients with radar cross-sections and all sorts of stuff like this. I'm trying to think of a better example in my world, but these are things we always try to get a relationship, some sort of a correlation, so we know how confident we are if we see certain types of behavior that signature is in fact what we think it is. And there's a lot more to it. Anyway, that said, now the best way to see how, okay, that's great. How does this apply? A great question. And the way I always do this is do problems. Apply it to problem, then you can see it, but I'm going to ask you questions about this and see how you respond. So, did anybody take a look at the problems in section 4? All right. Well, you did? Good. I'm glad. They're not hard, really, but they do bring out what you need to know. By the way, that formula, make sure you know. I'll put up some stuff on the PDF and the PowerPoint, and I'll try to make sure you understand that. He has a few other points. So, and let's see. I know you have the problem. So 3-4. Do you have that in front of you? How you doing? So this is 3-4.1. And here you've got two random variables, x and y, random variables, right?
Yeah.
And then, did they say they're statistically independent or not?
They said they have zero mean variance of 16. The correlation coefficient is 0.5.
All right, so they say rho xy is 0.5. All right, and what else did they say sigma x is what?
Variance is sigma x is 16.
Variance? Or sigma x squared is 16, and what is sigma y?
36.
All right, so right away I'm going to say this. That means sigma x is 4 and sigma y is 6, just so we keep our heads on straight. And what else did they say?
Zero mean.
Both of them?
Yep.
All right, so that's nice. Equals 0. All right, what do they want?
Find the variance of their sum.
Okay, so now what they want is the variance of x plus y. And I think there's one thing I've got to mention right here. See it right there, but anyway, how would you do a variance of their sum? What does that actually mean? Well, it's the expected value, right? Since the means are 0, it's the expected value of x plus y squared. Do you agree with that, class? Means are 0. Do you agree? That's their sum is x plus y because both have 0 mean. That would be the variance of their sum. First, does everybody see that? All right, what is that going to be? Well, that's the expected value of really x squared plus the expected value of y squared plus the expected value of 2xy. Do you agree? All right, and what's that going to be? Well, I'll go down here. So that's going to be equal to the expected value of x squared plus the expected value of y squared plus 2 times the expected value of xy. Agreed? I want to make sure everybody sees this. I'm doing this as simply as possible. All right. When I ask a question, by the way, when I ask stuff like this, oftentimes, what if I want the variance of x over y? Stuff like that will throw people. Then you just mathematically do what the variance says, right? You're going to take the expected value of x over y squared, follow me? And just break it up from there. Anyway, do you all follow me right here? Now, what is the expected value of x squared based on the statement of the problem?
Variance of x.
Right, and in general, what? When you talk about x squared bar, that's equal to sigma x squared plus the mean value squared, right? And if the mean, or the average value, if that's 0, then those two are the same. Do you agree, class? I want to make that point. So this is just going to be sigma x squared. I'm going to write it down first. This is going to be sigma y squared. And this, now how do I get that? Right, I'm going to rewrite that formula so it kind of gets ingrained in your mind. So the correlation coefficient between x and y is equal to the expected value of xy minus x bar y bar over sigma x sigma y. You'll get used to knowing that like the back of your hand. You can actually prove that from the definition a fundamental definition of what this correlation coefficient is. I'm going to start filling in things. All right. First, I'm going to break out expected value of x and y. And keep an eye on it. The expected value of x and y here is going to be rho of xy times sigma x times sigma y. And then I have to take this to the other side, so it's going to be plus x bar y bar. Just make sure everybody follows me. Right. It seems irritating at times, but I'm trying to I want to go slow and make this point as clear as I can. Okay. Now, based on what we know, we all agree we can get rid of those two. Mm-hmm. It doesn't always happen. I'm going to warn you, it gets much more complicated when you can't get rid of them. So now I have this, or now I have the expected value of x, y equal to the correlation coefficient, which is it 0.5?
Yeah, 0.
0.5. Sigma x 4 and sigma y 6, so it's 4 times 6, and that's 12, right? Do you agree with that? All right. Now, coming over here, that means this value is really going to be 12. I should have taken it down another notch. And I can say sigma x squared. Now you got what? 16 plus 36 plus 24. I believe that's right. And I think that is the right answer. Let's see, that's 676, is that right? And I think I may not post the answers to all of them, but let me see if I even did that when I came. Yeah,
76, yeah. Yep.
You agree with that, class? And you have the solution. I didn't post the other set of solutions, but you all agree with this, class? Yes, sir.
You were able to say that the variance of x plus y is just the expected value of x plus y squared because the means were 0, right?
That's right.
Okay.
Now, if it wasn't 0, then what would happen?
You'd have to add the mean
Well,
plus y.
let me just, because we're going to do this, but I'm going to state this and I'm going to show you how irritating it is. So then, if the means weren't 0, it would be the expected value of, really, if it's of x plus y, then you gotta go ahead, it's the expected value of x squared plus the expected value of y squared plus 2 times the expected value of x times y. Do you agree with that? All right, now what's this? Well, this is gonna be sigma x squared plus x bar squared, right? From over there.
Mhm.
This is gonna be sigma y squared plus y bar squared plus, and here, what's this gonna be? It's 2 times the expected value of x times y, and here, because there's a correlation coefficient that's not zero, you all see this? Now I gotta go over here, I erased that. Now I've gotta basically solve for e of x, y, and I have to take all that stuff over here and plug it in. Y'all follow me on this? So it gets more work. I mean, a lot more little things you have to account for and be careful of.
It's the same concept though, you're just using the mean in the equation.
Well, yeah, since the mean's zero, everything simplifies, right? I mean,
Right.
you get rid of that. And then everything, in my opinion, becomes a lot easier because you're gonna have, you can have a lot more terms than what I'm showing here, by the way. Because when we get to 3 variables or something, it's, like what if you have a sum of, say, z is x plus y plus like, or make it, I call it like gamma is x plus y plus z. Each random variables and both have, they all are correlated. Correlation coefficient xy, correlation coefficient xz, correlation coefficient yz. And you want the variance of z or you can figure out what you want. But now the equations just get enormously long. There are tricks to it. Back to this one. What was the second part? We got the first part. What did this say?
Find the variance of the difference.
Well, we're going to do that here. We'll do it right here. So now part B, they want the variance of their difference, x minus y. I'm assuming it's x minus y. Okay, well, as a class, we do that. What's my next step? Well, define, just do it this way. Do the expected value of x minus y, right, squared. Do you agree with that? And by the way, well, no, I'll leave it like, we'll just do this. So what is this gonna be? Expected value of x squared, right? Plus expected value of y squared plus, or actually what? Minus 2 times the expected value of xy. Agreed? You can see it's almost identical. We could have used that in prior work and just changed the sign, right? What happens now? Since the mean values are 0, it's sigma x squared plus sigma y squared, right? Minus 2, and what was the expected value of x? What did I write? 12. That's right. And that's what? 16 plus 36 minus 12. So, pardon. And that's going to be
Be minus 24.
40, what?
That'd be minus 24.
Or, I'm sorry, minus 24, my bad. You're right. Minus 24. $28.
Yep.
And, see, I don't know the answer. Yeah, that's it. But that's sort of the deal with how you go about these. That's a very simple problem, but things are gonna get a little more complicated. I wanna do the next problem too. I know I do these problems, and sometimes it's almost boring. there are certain things in here that, just in my opinion, you can trip over. They're things you can just kind of relax, not focus on, then you'll miss something. Do you have a test today or anything? Nothing? Okay, good. When's our next day off, or don't we have it?
I don't
think we have it.
What's that?
I don't think we have any.
So we're finally gonna have
Mm-hmm.
classes on schedule. Yeah, a lot of days off.
Mm-hmm.
I don't remember if summer had that many days off in a month's time. All right, so 3-4.2.
Two statistically independent random variables.
Independent?
Mhm.
Okay, X and Y?
Yep.
All right, there, which is nice. Statistically independent means rho xy equals 0. This is important. If they're statistically independent, the correlation coefficient is 0. And did I say that before? No, probably not. But I was trying to show you in the graph if there's no relationship, it's 0.
Mm-hmm.
It is also 0. It's a flat line if y doesn't change. But go ahead.
They have variance of x is 9,
Hold. A variance of is what?
9,
And y?
25.
Okay, let me just do this. Sigma x is 3, sigma y is 5. Go ahead.
Two new random variables are defined by
This is weird. Go ahead.
u equals 3x plus 4y.
Go ahead.
V is equal to 5x minus 2y.
Minus what?
2y.
Okay. And what do they want?
Find the variances of u and v.
All right, so they want, A is variance of u and variance of v. Okay, guys? Did they say anything about the mean values?
No.
Okay. How do we get this? That's a good point. Variance of u and variance of v. And what's the next part, by the way?
Correlation coefficient of u and v.
Okay. Well, how do I get this?
The expected value of u squared.
Yeah, put it over here. When I want the variance, what I'm really looking for is the expected value of u, right there, minus u bar, right, squared. Do you agree with that?
Mm-hmm.
That is expected value of u squared, right? And then it's going to be plus the expected value of u bar, and the whole thing squared. Let me just do it this way. Just put u bar squared, and then it's going to be minus 2 times the expected value of u times u bar. Yeah, okay. First, do you agree with that? Right?
Mm-hmm.
Okay. Let's keep going on this one. So, when I look at this, because u bar is a constant, this right here, I can go ahead and right off the bat, I can say this is the expected value of u squared plus u bar squared, and then it's going to be minus 2. Now, the u bar is a constant. I can take it out in front. The expected value of u is u bar, so it's going to be minus u bar squared. You agree with that? Do y'all follow me what I'm doing here? Because look, here, u bar is a constant. We don't know what it is, but it's a constant. It can come out. Therefore, the expected value of u is u bar. That means this is 2 u bar squared. Do you agree with this, class? If that's the case, down here, it becomes the expected value of u squared, and then here, you're gonna get plus, actually, sorry, minus u bar squared. And then I have to do what u squared is, and because u is that, I'm gonna go here. And I'm going to show you something. This is going to be expected value of, going to be 9x squared plus 16y squared plus 24 times xy. And that is 9 times expected value of x squared plus 16 times the expected value of y squared plus 24 times the expected value of x times y. Right, so we're going to see that there's a way to get a correlation coefficient for all this stuff, but
Do you agree with that, class?
we're just doing the math on this. So then, erase over here, since we're after the variance of u and v, but this is going to be equal to, take this whole thing, that means expected value of u squared is equal to 9 times sigma x squared plus x bar squared plus 16 times sigma y squared plus y bar squared plus 24 times and I believe that's right. So the expected value of u squared is going to be, now I gotta break out the terms I care about. So I have 9 sigma x squared plus 16 sigma y squared. Then I'm gonna have plus 9x squared, or bar squared, plus 16y bar squared, and then plus 24. And here's the kicker. Correlation coefficient is zero right here. So what I can do is say, put it over here. Because the correlation coefficient of xy is 0, and that's the expected value of xy minus the expected value of x bar, y bar over sigma x times sigma y. And because that's 0, I can end up finding this. Y'all, you know what I'm doing right here. Just rewrite. So because that's 0, multiplying by sigma x sigma y gives that, or I can say the expected value of xy is equal to simply expected value of x bar y bar is x bar y bar. Just you all agree with this, class? Back over here, that means this becomes x bar, y bar, and yeah, I got it. maps it. Okay. All right, I've got down to this point. And one thing you can see is, here, we got sigma x, we got sigma y. What we don't have is anything about these average, or the mean values. However, there's something, and this is in the book. I'm going to show you this. Sorry, I kind of went the long route on this. Let me put this here. So, and I'll tell you what page it's on to. Let's try to go down and make a point that if you follow it just rigorously down there, you're going to come to an odd ending where you really have to fuss with that to get it right. But now, I can find it. Oh, yeah. But he doesn't put there. Give me 1 second. There's part of this on page 135. It's formula, write this down to 3-28. The problem is, it didn't include these coefficients. Let me find out. Give us a second. Put this down. He, on this page 135, he's going through and he develops something, but the one thing he doesn't do is put the coefficients in there. I'm going to put this down and explain what I'm talking about. So if you want the variance of actually, let me put it right here. Make sure you can all see this. So if you want the variance of ax plus by, please write this down. And the variance, so it's going to be this squared, or maybe I should put it like this squared. That's going to be equal to a squared sigma x squared plus b squared sigma y squared. And then it's going to be plus 2a times b sigma x sigma y. Now in his book, he doesn't have these coefficients. All right, but this will be the variance. So get rid of that. When I came down to this point, if you actually get down to this point, I believe, because x and y, the way that he does it in the proof there, he's going to find a way to get rid of this entire term, and there'll be a second term right there that accounts for it, that includes this right here. He's going to basically factor that whole thing. But this is the key thing. This is the variance of any equation ax plus by, and we have that right there. Now we're going to use this. Can you all read that, what I've got there? Okay, write that down. I'm going to come back over here, and I'm going to say, he asked for the variance of this, right? This one? If he wants the variance of it, because I forgot this, when I subtract off the u bar, all that will go away. But the variance in the equation was 3x plus 4y. It's going to be equal to sigma of 3x plus 4y squared And that's gonna be 3 squared times sigma x squared plus 4 squared times sigma y squared plus, and then it's gonna be 2 times 3 times 4 sigma x sigma y with rho xy. I'm putting it down like that. Do y'all follow me? But what's the key? Rho of xy was 0, right? And if rho xy is 0, this goes away. I shouldn't have spent that much time, but that means for this one, sigma of u squared, the variance of u is just going to be 3 squared sigma x squared plus 4 squared sigma y squared, and that's 9. 9 times 9, which is okay, plus 16 times 25. Let's see, you got 81, 7, wrote it down. That should be 481. Y'all follow me on this one, class? I didn't mean to waste that much time, but let's try and make one simple point, that if you go this route and then you have to find what U bar is over there and do it, it's a long, lengthy process, and it's much easier to just use this form. This form is proven. Yes, sir?
Where did the rho xy come from on the end?
Right here in the statement of the problem, it says that they were statistically independent, and if they are, the coefficient, rho of xy between x and y, the correlation coefficient is 0. That's what's, when they say.
Right, but where did it come from in the equation? Because it's not on that side. Where
It's
you-
right here, rho of xy.
Yeah, is that supposed to be over there too?
That's right. Oh, thank you. I'm so sorry. Thank you very much. Now, in the book, he doesn't have the coefficients A and B, and that's a problem in that formula. So make sure you get that formula. You really need to know this, because this will save your life in a lot of ways. It's a long, drawn-out process. When you go that way, you'll get the right answer, but at least in my opinion, it takes way too long. Are you with me on that? And I believe that's the right answer between the solutions, if you look. I'm certain about that. Now, what about the next one? For what correlation coefficient, or the variance, variance of V. How do you get that? I'm just asking everybody, because I'm trying to make you at least think. You don't have to respond necessarily, but think.
Gonna use the equation again, but with the new.
We're going to do the same thing, the same exact thing. I'm just going to say this right here will be equal to sigma of now, that's 5, be careful that sign, that minus sign, by the way, 5x minus 2y squared. And that's going to be equal to, and I'm going to do the same thing one more time. So it's going to be 5 squared, 25. Well, maybe I better write it down. So it's going to be 5 squared times sigma x squared. Then it's going to be plus minus 2 squared times sigma y squared. Then technically it's plus 2 rho xy times a times b, or times 5 times minus 2 times sigma x, sigma y. I'm writing it down. You all know, I'm just taking that formula, I should have written it a little larger, and I'm simply putting in the values, but what's the key on this one?
The rho x.
Rho xy is 0. Do you agree with that? And so just get rid of that, right? I'm gonna just cross it out. And that means this is, what, 25 times sigma x, 25 times 9, and then it's gonna be plus 4 times sigma y is 25. I don't know what that is, it's 100. And then 25, is that right?
325?
I think so. I think that's right. 325.
Mm-hmm.
Okay, spent a lot of time with that. Now we're going to the next part. First, you all follow me on this, class? What's going on? This one's tricky. This one is tricky. You can ask yourself how you do it, but I'll put it right here. Try to it later. So, in this part, I think it's C, maybe it's B, but
It's B.
it's B.
Correlation coefficient between U and V.
All right, now this one's a little different. So how do I get rho of UV?
Expected value of U times V minus mean of U times mean of V over.
It's expected value, or the correlation coefficient between U and V, correct? All right. And, okay. I'm gonna go, how do you go ahead and get that? I'm gonna write down the general form. Here's the normal way to do this. You would say, well, rho of anything, xy, of u, v, is equal to the expected value of u times v minus u bar v bar over sigma u sigma v. You agree with that? And if you did that, you're gonna kind of go down a long, hard road. But if you go ahead and create a variable, try to do this simply. If I create a variable z, this is the trick on this one. And I'm going to let z equal to u, and it's going to be plus 2v. Y'all follow me on this? Now, what you're going to find out here is z is equal to u, 3x plus 4y. Here's the reason I did this. And it's going to be plus 2 times v, so it's also going to add to that 10x minus 4y. Y'all follow me? Here's the idea. I want to get rid of one of these two. I want this thing, this new variable, to be a function of only one, either y or x. Do y'all follow me, class? And you're going to see why in a second. But when I do that, now I have z is equal to 13x, period. Follow me? And if you look at that, that means the standard deviation of z is equal to 13 squared times, or I should say variance is e times sigma x squared. And if you look at that, we have this. And that is, this value is sigma of oh, here it is. Z is u u plus 2v. So that's sigma of 2u, or I'm sorry, of u plus 2v. And that is equal to sigma u squared plus 4 times sigma v squared, and then it's going to be plus 2 times 1 times 2, or 2 times 2 times sigma u, sigma v, times the correlation coefficient of uv. I'm going to stop for a second. Y'all follow me what I'm up to? Here's the idea. If I try to do this, I'm going to, just like before, this thing's going to expand out to a mess. All right, when you put the values of u, I mean, basically substitute 3x and 4y and 5x minus 2y. But I know one thing, if I can create a variable that's only a function of x or y, now I can get something where this sigma z squared is going to be that. Do y'all first agree with that? Right? Because, you know, if you have, like, any equation, if you have x equal ay, sigma x squared is going to be a squared sigma y squared. It's always going to be that relationship. It's a linear relationship. Follow me on this? So, y'all see how I've got this, don't I? Right? I have sigma u, we just calculated that. Agree, sorry, the variance of u, and we have the variance of v. We have we have standard deviation of u and v. We don't have that. Now we can get that. Y'all follow? By the way, this is tricky, because when on test, if I give you something like this on a quiz, people fumble with these things because they don't know. They will go down this route, in this route.
How did you get the z is equal to u plus tv?
Why did I do this? A better question. Why? Because I want to create I want to create a new variable that's only a function of either x or y. See how both of these are x and y? So I'm going to, this is the way I get, I'm going to scale this thing by a factor of 2. So if I take u plus 2v, all right, I get 3x plus 10x. And then, you know, I got 4y minus 4y, the y's cancel. That's the game I'm playing here. Otherwise, it gets, you go down this route, all right, you can do it at the end, but it's an incredible mess. This is the easy one, just remember this.
And that's a sigma times u plus 2v.
This is squared, actually. It's the variance of the it's the variance of z. See, that's the variance of z. I replace z with the actual formula I used. And that way I can get the correlation coefficient between u and v. That was my goal.
Which sigma are you using?
What?
Is that sigma z?
Here, this is sigma z squared is 13 squared sigma x squared based on that. That's the reason I scaled these things the way I did, is so I get z is 13x. And that means I have sigma z squared, or sigma, really, the variance of z is 13 squared times the variance of x. So that means I've got this one here. Now, if I have that one, I can go ahead and use the formula I put up a second ago. Follow me on this? And I can say, well, that's going to be, since 1 is there, it's just 1 times sigma u squared plus, you have to take 2 square it times sigma v squared, right? And then you have to take 2 times this coefficient, 1 times 2, or just 2, times u, sigma v times rho uv. Now we can calculate rho uv. We're about to. And I know this seems irritating, but this is the nature of this section. The problems are irritating. They're not that hard, but the trick is always getting rid of, whenever you have something like this, you get equations, getting it down to a new variable that has only one function of either x or y. You can do it with y too on this one. It doesn't have to be x. Anyway, back to this thing. Now we need to solve for that. So let's take that sigma e, or rho of see, the easiest way, I'm gonna put 13 squared times sigma x squared, that's that side. Then on this side, I'm gonna subtract some of these things, minus sigma of u squared minus 4 times sigma of v squared. And then I'm gonna have to take that, all that stuff, and divide it by 4 times sigma of u, sigma of v, to get rho of uv. Y'all follow me on this? I'm just trying to solve for the correlation coefficient. By the way, some of these things I'll level with you. If you aren't real careful, you can make silly errors like I did leaving that row out there, and it just fouls up everything. All right, so you gotta help me to write this. I got 13 squared, and sigma x is 9, and then it's gonna be minus, what is sigma u? I forgot, sigma u squared, the variance of u, 481?
Yeah.
Minus 481, and then minus 4 times, is this 325? All right, down here, 4 times, and this is gonna be square root of 481 times 325. Good luck doing that in your head. And so what is this? I hate to have no calculator test this. Can everybody do that to me? Did you do this problem, by the way? Did you get the right answer on this?
I did it a completely different way. But I did get the right answer on it.
Did you go through the long run?
Mm-hmm.
That takes a long time. I mean, it didn't for you?
Not with this calculator, because I can expand on it.
Oh, never mind. Okay. Maybe you should show the class how to do that. Anybody?
Where did the square root come from?
Because remember, see, this is u, sigma v. Well, sigma u squared is 481, and sigma v squared is 325, right? So I have to take the square roots of both and just put them both under square root.
I got,
Single square root.
I got minus 0.1644.
Minus 0.164. Anybody confirm?
Yeah.
All right, now I want to tell you one other thing. I didn't say this earlier, I don't think. Rho, the correlation coefficient, because of the scaling with sigma x and sigma y, the correlation coefficient will always be between -1 and +1, and it can be any value in between there. It'll never, if you get a correlation coefficient of 2 or -2 or anything like that, something's wrong. You can't have that. Correlation coefficients mathematically can be from -1 to +1, and that's it. And you can't have an imaginary value for that, by the way. There's weird things where people will get the square root of a negative number somehow, and they'll have a j, or plus or minus j, and you can't. Okay, is there another part to this one? Oh, what am I doing? I gotta give you the book. Here.
So that's like a reflection coefficient, like either it can reflect all of it,
Well,
or
you're
like,
thinking
that's like
Emacs.
the other one.
This isn't exactly a reflection coefficient to the relationship, but you're right, reflection coefficient Emag, maximum value of 1, minimum value of -1. It can't be 3. Or the only way it can be is if you have an active, it's called an active material that can add energy. And that's way out of your range of what you can talk about. You can ask Ben Smith about that. Caught him some angst.
Where's that?
Okay. by the way, for the variance, did I do that part of UP? Yeah, I did. I think I did. Yes, I believe I did that part. If I didn't, for the next one, this is 3-4.3. Is that, did I post that solution for that one? Can anybody tell me?
3-4.3.
Yeah.
Yeah, you did.
All right, now, you can see that these problems are getting progressively more involved. They're really not getting that much more complicated in the sense that real abstract theories are coming out. But the way to go about solving them, at least the way I did this, if you did it the long way, if your calculator will do that, there are probably others here that would like to know how that calculator did that, because that's the easiest way I know to do it. The long way is going that way. Anyway, next part. You know, I don't remember if that PowerPoint, Denny's PowerPoint has any example problems like these for this section. But here, the next, after this problem, the next thing is we go right into section 3-5. Okay, for this one, just work it with me. It's 3-4.3, right? What does it say?
A random variable x has a variance of 9, and a statistically independent random variable y has a variance of 25.
Sigma x equals 3, sigma y equals 5, and rho of xy equals 0 because they're statistically independent. You agree with that, class? Based on the statement of the problem. He said it does say statistically, but it doesn't say anything about zero means, right? So we don't know the mean of x or mean of y. Go ahead.
Their sum is another random variable z is equal to x plus y.
Equals x plus y. Go ahead.
Without assuming that either random variable has 0 mean, find the correlation coefficient for x and y.
All right. Now, you ready? First of all, sigma of the z squared is really sigma of x plus y squared. You all agree with that?
Mhm.
All right. And this is equal to sigma x squared plus sigma y squared. And then it's going to be plus the correlation coefficient of xy, plus 2 times the correlation coefficient of xy times sigma x times sigma y. First, y'all agree with that? Now, it's statistically, x and y are statistically independent, right? Get rid of that part. That means sigma x squared, 9, so it's going to be 9 plus 25, or 34, would be sigma z squared. Do you agree with that? And is that one of the questions? Refresh my memory. Oh, correlation coefficient. Is that,
Yeah, the first question was correlation coefficient.
of
X and y.
is 0. Do y'all follow me? By definition, sorry.
No, the last one is variance of z, so that is one.
All right, that's the variance of z. Can anybody confirm that answer, by the way? I don't remember.
That's what it says on one note.
All right, and what's the next question?
Correlation coefficient of y and z.
Now, so now they want the correlation coefficient of y and z. So really what they're looking for is, and I'm going to try to do it this way, sigma of y plus z squared. First, do you all agree with this?
Mhm.
We can go ahead and expand this, because we want, the function I'm putting here is y plus e, even though z is a function of y and x. Don't worry, I just want to make sure you see this. You with me, class? We break this out, and we get, that's going to be sigma y squared plus sigma z squared. And then it's going to be plus 2 rho yz times sigma y sigma z. Agree? Okay. And we want that correlation coefficient, so this right here is going to be what? Actually, let me expand this. So sigma y plus x plus y squared is going to be sigma of 2, or of really x plus 2y squared, and that's going to be equal to sigma x squared plus 4 times sigma y squared. I'm going to write it down, plus 2 times rho of xy, sigma x, sigma y. And then it's going to be times another 2 here, technically. What I'm doing is expanding that, but the key is what in this part? Do you all agree that's the right equation? What's the one thing we can do to make life easier? Rho of xy is 0. That's the whole point. The reason I wrote it down. So that goes away, and that means this is sigma x squared all right, wait a second. What is sigma x again?
9 is sigma x squared, and 25 is sigma y squared.
So that's going to be in 100, right? So is that like 109? So that means this right here is 109, right? And then if we want the correlation coefficient, let me do this because I got a few minutes. The only thing I need to do is solve for that. Do you agree with that? And doing so, we're going to get rho of yz equal to 109 minus sigma, I'm going to leave it as sigma y for now, minus sigma z squared all over 2 sigma y sigma z, and now simply 109 minus 25 minus, what was sigma z again, 34 over 2 times square root of 25 times 34. I, for the life of me, can't do that one. What is that? You don't follow the method though?
Mm-hmm.
But you need to be aware of this, that when you write, when I did this, I expanded what z was, and because it's x plus y, you're going to get 2 y's. So it just is another use of that formula I had over there in the beginning, or earlier. What is this?
No, 0.857.
0.857? Did anybody, can you confirm that? Is that the answer, by the way?
Yes.
So, all right. And what's the next part? I'm just gonna,
The last part was variance of z.
we got that. All right. So you good with that, class? What I want you to do for homework, and I think I beat this one to death. I want you to do 3-4.4, but I have a comment. And I don't know what the solutions manual has for this. I haven't looked at this, but when they create a variable, w, x plus y plus z, do y'all see that? He's trying to slowly complicate things. He's expanding the level of difficulty and he's curious. When you do that, the key is 3 zero means and unit variances. Underline that, that's the key. When you go ahead and do this, like the variances and all that stuff, it will kind of, it'll be easier. But do that problem for sure for homework, okay? Make sure you know how to do it. Now into section 3-5. Let me see if I can pull up a PowerPoint because I'm not going to have enough time on the board to do some of this stuff. I gotta ask you, is it helpful when I work problems, or would you rather just go through? Honestly, these problems sometimes, there's a couple coming up that I don't think the solution is doesn't hurt. They're difficult. This is one thing I want to make sure I say. You see right here where the air cursor is? That's the formula I tried to put up in the beginning, but I forgot that this row, but it's really a squared sigma x squared plus b squared sigma y squared plus 2ab sigma x sigma y times the correlation coefficient between x and y. This is critical. And you'll notice that these are additive down there. So if you want the actual variance of two variables, I want to say one other thing. You see this formula right here? This is just squaring ax plus by and squaring it out and taking the variance of them. Follow me on this class, or the standard deviations. If you had three variables, like in that one, just listen. If you had ax plus by, and then it would be like plus cz or something like that, go ahead and just square that. And you're going to get terms, you're going to get, I think you get 6 terms on that one, I don't remember, but it's longer, but it's the same form. Y'all got me on that? That's, for that last problem, you can do it that way. This is only a 2-variable form of this. Okay, enough said about that. These are the problems that I gave you before you went to break, but I didn't expect a lot of people to do them because you're on break. Back to this. Now, this is the density of when you have the sum of 2 random variables, but this gets important. So this is the density function, not the correlation coefficient, but the density function for z. If you had x and y, whether they're statistically independent or not, and you create a new variable, z, and you want the probability density function for z, how do you do it? Well, you're going to have to look at this carefully. I'll try to, at the end of the day, I'm going to break it down exactly what the easy way to do it. But he's saying, well, the probability of z being less than some value z is the probability of x and y less than z. You can see that there's a straight line. Z itself equal to x plus y. There's going to be a region. Can you all follow me on this class? If you make, if you make x and y 0, it's right there. But if you keep expanding it, it's going to be like this. It's a triangular region. And you probably remember doing something like this in calculus, which you have to calculate areas and things like that with different form of equations. So like y here would be x minus z, you all follow? And that's gonna have a negative slope. Anyway, when you look at this, if you take joint density function of x and y, integrate out x, and then you integrate y, basically x is going from minus infinity to z minus y. So it's going from minus infinity to here, and then y he shows going from minus infinity to infinity. You get the probability density, or excuse me, cumulative density function for f of z. Now, if they're statistically independent, you can break it up like this. That's not going to mean a whole lot to you until you see it used, but the real thing is this, the differentiation of this. Now listen to me. Right? On for one second. Here, this part states explicitly they're assumed x and y are statistically independent. If that's the case, I want you to take, this is just there's a form of the differentiation, Leibniz rule, and basically when you go ahead and do that, you end up with this. Now take a good look at this right here. That is convolution. If you have two functions, f of y and f of x, do you remember to do convolution? It would be like the first function, f of y of tau times f of x of t minus tau, or do you remember, I should say t minus tau, d tau, and integrate that. When you did convolution, that's exactly what you did, if you recall. Do you remember that, the flip and shift thing? That's what this is. And here, Denny even says it explicitly. So if you have density functions for x and y, and the third variable z, that's equal to x plus y, it's real important to understand this. You can look through the actual proof on this one. It's simply the convolution of the two density functions. The problem with these things is, when you're doing convolution of density functions, oftentimes there's several different regions that you had to consider the convolution's value on. Y'all remember doing that things? And you got to be careful with this, because it's not usually one answer over all possible values. It's usually multiple answers with regions where it's actually valid. This is a fundamental formula for convolution he uses. If it's actually, do you remember? You know what the term for this is? If you have z is x minus y, you get this. You see how the difference is, instead of a minus right there, it's a plus. This is called correlation. Now, either one of these things you can do, but the thing about this one is correlation doesn't require you to flip. You remember when I think you were taught this in convolution. It was, whichever one has the most going on, you leave it alone, just trace it out, and you're going to have a variable here. The other one, you're going to flip the other function, and you're going to flip, and then you're going to shift it through the region, look at the overlap area, do a point-by-point multiplication, and integrate it. Well, with correlation, you don't do the flip. That's the only thing. You're not going to appreciate this until you see some problems. Real quick, I'm over. All right, I'm going to ask you to go through and at least touch base on section 5, because this stuff, convolution, irritates me. I'm level with you. When I taught signals and systems for years, convolution was the one sore point in that course. More people hated that than anybody. I don't want to read it. Okay. If you got questions, let me know. I'm going to put some homework up for this. We'll do the problems, but we'll warn you about this one. There's a lot more irritating.